Okay, so in this video, we're going to continue thinking about multi-part quantum systems, and I'm going to introduce the idea of entanglement. And so our setup is that we have system one, which may be some particular system that we're interested in, which is in the context of a larger physical system. And system two here represents all of the other degrees of freedom. And so like in the last video, we're going to assume that system one is described by a Hilbert space with basis elements that we label by this little n. And we'll assume that the dimension of the Hilbert space for system one is D1. And similarly for system two, the basis is going to be this set of elements labeled by a capital N, where capital N runs from 1 to D2, the dimension of the Hilbert space for that second part. And so in the last video, we said that we can describe the basis of states for our combined system in this notation n, and then the fancy multiplication symbol is called a tensor product, and so n, little n tensor big N, and all that means is we define a state, a particular basis element for our larger system by pairing up these basis elements for the smaller system. And so so far that fancy multiplication symbol is just an operation that takes a basis element from the first system and a basis element from the second system and gives us a basis element for our combined system. Now we can make a more general operation out of this basic operation. We can define an operation that takes any state of system one and any state of system two and gives us some state of the combined system. And the way we can do that is simply to assume that this multiplication symbol has a distributive property. And so for example, if we have a system of two spins, then we could take this state of the first system and let's say just a simple state of the second system. And now the way to interpret that is just to assume the distributive property, multiply everything out, and so that gives me 1 over root 2 up cross down plus 1 over root 2 down tensor down. And then we see that this is a state of our combined system because it's a linear combination of basis elements of our combined system. Okay. Now, the most important thing to understand in this video is that not all states of the combined system can be represented in this way. Okay. Represented. So let me give you just a quick argument for that. So we'll call these states that I can represent in this way, I'll call them product states. So in general, if I have my two quantum systems, then the product states would look like this. And if I multiply that out, that would be a sum over n and n. And then the product of these two coefficients, and then some basis element. And what we notice is that the number of coefficients that I needed to represent this general product state is, sorry, not n1 plus n2, is d1 plus d2 coefficients. Okay, so we have we have D1 coefficients to describe the state of our first system, and then D2 coefficients to describe the state of our second system. And so the total information we need to specify that general product state would be D1 plus D2 coefficients. Now let's think of the general state of our system. So the most general state of a two-part system, we said, well, we need a coefficient for every possible basis element. So it's just a general linear combination of our basis elements. And what you'll notice is that we actually need D1 times D2 coefficients, because our coefficient here is labeled by those two numbers. Okay, and we have to choose the first number and we have to choose the second number, and there's D1 times D2 ways of doing that. Okay, and so we see that there's just a lot more information that we require in order to describe the general state compared to describing the product states. Okay, so there must be a lot of states that can't be written as a product state, and this is actually how we define entanglement in quantum systems. And so any state that cannot be written as a product state is defined to be entangled. And so the entanglement is between our system 1 and the remainder of the system, which we call 2. And so just as examples, so it's easy to write down some states that are not entangled. So up, down, that's just one of our basis elements, and that's clearly not entangled because it's written as a product. We can have slightly more interesting examples of states which are not entangled. So an example would be this state. That's actually the one we wrote up here, and that is clearly not entangled because I can write it as a product of this state with this state. Okay, so it's also not entangled. But we can give an example of a state that is entangled. So let's say we have 1 over root 2 up, down, minus 1 over root 2 down, up. And so that one, you can try to write it as a product of a state of system 1 and a state of system 2, but you will fail because there is no way to write it as a product. And so this state is an example of an entangled state. Okay, and just to emphasize, for general quantum systems, if I have a two-part system, then almost all of the states that I can write down are entangled. So these states that are not entangled are actually very, very special. Okay, and so in the next video, we're going to talk about when I do have an entangled state, how can I represent the information about just one part of that state? So when I have a state that's not entangled, then it's obvious that there's some particular state that the first system is in. But it's actually more subtle when I have a combined system that is entangled. If I want to just describe the first part of the system, it's a little bit subtle how I can do that.